First, let me introduce myself. I am A.K. Misra and a retired faculty from IMSC here. And to begin with, I will invite Professor Ramanujam to say a few words about our institute. Please.
Thanks, Professor Mishra. I'm Ramanujam from this institute, and it's my pleasure to welcome you all to this day of excitement in science. As you probably know, this is an institute of. You heard all that in the video. It's a research institute, an autonomous research institute supported by the Department of Atomic Energy, and it has groups working in mathematics, theoretical physics, theoretical computer science, and computational biology. Please take a look at our website and look at the programs. And at this juncture, I wanted to mention, like this today's event, there are many outreach events that happen in the institute. Every year we have programs dedicated to high school students, undergraduate students, postgraduate students, and then many graduate courses at different levels. And then we also have programs for teachers at high school level, higher secondary level, college teachers. So we have annual programs almost every year. Right now, in fact, we had one which just concluded for teacher of mathematics from engineering college. So there is a regular component by which the institute interacts with students and teachers in the city. And this is something that we are very particular about. And among these, we also have many lectures communicating science to the general public, and especially the student community. And as a part of this, today we have this an excellent program covering a range of topics, and with the International Academy of Physics. So it's a pleasure to have you all here. As Professor Mishra said, on a day of terrible weather and with the heavy rains, I'm very happy that you have come. And I assure you that you're going to have some very exciting science to look forward to. Thank you very much.
Dear students, research scholars, and fellow colleagues from many colleges, universities, and institutes, you are welcomed here. We have assembled here to participate in a one-day meeting on excitement in science. First of all, on behalf of the organizing committee and convener, I would like to thank Professor Arvind, our director, for fully sponsoring this meeting. We are fortunate that a number of very distinguished professors and scientists, Professor Rajasekaran, Professor Balasubramanian, Professor Madhavan Mukund, Professor Sitabra Sudha, and Dr. K. Ramesa have consented to participate in this meeting and deliver talk on their area of specialization. We hope this will enthuse younger participants here to get inspired and motivated towards a scientific research field. This meeting is in celebration of 25th anniversary of the International Academy of Physical Sciences, IAPS Allahabad. In fact, the Academy has planned such meetings in each state of India, from Jammu and Kashmir to Tamil Nadu and from Gujarat to Meghalaya, as a part of its Silver Jubilee celebration. And at the present count, 28 states have been covered in this function. So very briefly, I will sketch a brief sketch I will provide about the IAPS. And basically it caters to an interdisciplinary scientific community. So what was the motivation for this organization, this academy? So what they found that with the growth of scientific knowledge and our experiences of its application for the betterment of human society, it is becoming increasingly difficult to draw a sharp line to differentiate between the various branches of physical sciences. Thereafter, it was felt necessary to have a common platform for interactive discussions and interdisciplinary approach among scientists involved in the pursuit of knowledge in different subjects. So, to meet this necessity, International Academy of Physical Sciences was founded with its headquarters at Allahabad on December 4, 1994. Academy is conceived as a scientific body incorporating various branches of physical sciences such as physics, chemistry, mathematics, statistics, computer science, earth sciences, and biological sciences. The IAPS is a scientific organization of recent origin, but it had already made a mark by involving in it a large number of scientists, academicians, and researchers from India and abroad through their program like membership, fellowships, Young Scientist Award, annual conferences, and other activities. For the expansion of scientific knowledge, the Academy is publishing continuously the Journal of International Academy of Physical Sciences since 1997 and also collaborating with different universities and institutes of repute. So, this is a brief description of this academy. And now, if you look at the structure of this meeting, we see that each discipline physics, chemistry, mathematics, biology, computer science is being represented here. Thus, this meeting is in conformity with the spirit of the academy. So, with this brief introduction, now I will request Professor Rajaji to give a talk, but before that, let me introduce him. A brief introduction. Professor G. Rajasekaran, we call him Rajaji, is indeed means Bhishma Pitama of Indian high energy physics community. Apart from being an excellent researcher, he is an able institution builder. He is currently affiliated to both IMSC and Chennai Mathematical Institute. After his BSc from Madras Christian College, Chennai, he joined the first batch of Training School of Atomic Energy Establishment, Bombay, which is now known as BRC, in 1957 and obtained their first rank. He was awarded the PhD degree from University of Chicago in 1964. During his academic career, he has been associated with Tata Institute of Fundamental Research, Madras University, Institute of Mathematical Sciences as Joint Director, and Chennai Mathematical Institute. His field of research is quantum field theory and high energy physics. From 2001 onward, he is deeply involved in the creation of India-based neutrino observatory. Then he has got very many awards and recognition. He is fellow of all the three major academies in India: Indian Academy of Sciences, Bangalore; Indian National Science Academy, New Delhi; and National Academy of Sciences, Allahabad. And he is also recipient of very prestigious awards like Meghnad Saha Award for Theoretical Sciences, Federation of Indian Council of Commerce and Industry, FICCI Award for Physical Sciences, S.N. Bose Medal of the INSA. He has been invited by many universities and academic institutes in USA, Canada, and Japan, and he has made very fundamental contribution to the area of physics. We will now get a glimpse of his scholarship and depth and breadth of his knowledge from his talk on 100 years of fundamental physics and a crisis. Rajaji.
Good morning to everybody. I first of all thank Professor Mishra for giving me this opportunity to talk to you. Without further ado, let us start the talk. Which I have titled 100 Years of Fundamental Physics and a Crisis. Doesn't move. doesn't go to the next one. Battery pickup is China. So maybe I have to use this then. Shall I try to use this one? Ah, good. 100 years of fundamental physics have culminated in a theory which is called standard model of high energy physics. This theory is now known to be the basis of almost all of known physics except gravity. This is the most important sentence here. This is the basis of all of known physics except gravity. So anybody who wants to learn even a little bit of physics has to know a little bit of standard model. Although the discovery of the Higgs boson in 2012 is established this theory, gravitational force has been left out of this theory. The energy scale of quantum gravity, known as the Planck scale, is 16 orders of magnitude higher than the presently accessible highest energy, namely TeV. TeV is 10 power 12 electron volt. So 16 orders of magnitude means 10 power 28 electron volt. So that is the crisis in fundamental physics, how to reach that high energy. This is a crisis in fundamental physics that can be met only by the discovery of new principles of acceleration. So I will try to highlight this issue. "100 years of fundamental physics." The earlier part of the 20th century was marked by two revolutions that rocked the foundations of physics. Almost all of you would know about them. One, quantum mechanics. Second, relativity. Quantum mechanics became the basis for understanding atoms, and then coupled with special relativity, quantum mechanics provided the framework for understanding the atomic nucleus and what lies inside. At the beginning of the 20th century, namely more than 100 years ago, the search for the understanding of the atom topped the agenda of fundamental physics. This search successively led to the unraveling of the nucleus and then to the nucleon, namely proton or neutron. Now we know that the nucleon itself is made of 3 quarks. This is the level to which we have descended at the end of the 20th century. The depth of the descent scale probed thus far is 10 power minus 17 centimeter. That is what you should take home. 10 power minus 17 centimeter. We now know fundamental physics down to the length scale of 10 power minus 17 centimeter. So this inward bound journey has been captured in this box below. We started with atoms more than 100 years ago. Dimension 10 power minus 8 centimeter, went through nuclei of dimension 10 power minus 12 centimeter, then nucleons of dimension 10 power minus 13 centimeter, and we have reached that 10 power minus 17 centimeter. At this level, the quarks as well as the electrons seem to be point particles. What lies inside? That is a question mark. We do not know. The world's highest, the most powerful microscope, which is the Large Hadron Collider at St. Geneva, might discover what is lying inside, but that is for the future. This inward bound path of discovery, unraveling the mysteries of matter and the forces holding it together at deeper and ever deeper levels, has culminated at the end of the 20th century in the theory of fundamental forces based on non-abelian gauge fields, which I will explain what it is, for which we have given a rather dull name, standard model of high energy physics. I hope somebody invents a better name for this. In this theory, the strong forces operating within the nuclei and within the nucleons themselves, as well as the big forces that were revealed through the discovery of radioactivity 100 years ago, are all understood to be generalizations of the electrodynamics of Faraday and Maxwell. Those of you who are MSc students will certainly learn Faraday and Maxwell if you have not, electrodynamics of Faraday and Maxwell if you have not learned it already. So that is good news, because what I am going to talk about is a generalization of that. So electrodynamics was worked out by the year 1875, and the 20th century owes a lot to this electrodynamics, Faraday Maxwell electrodynamics, for the applications of electrodynamic technology, starting with wireless. Almost everything we touch now uses electricity and magnetism. One cannot imagine a world without it now. They have all become a part of modern life. And now I said, the standard model of high energy physics, which is the dynamics of strong and weak forces, is a generalization of electrodynamics. It turns out that exactly almost 100 years later, 1975, this theory also was completed. So the moral is obvious. Equally profound applications will follow once the technologies of strong and weak forces are mastered. What we are doing now is only to scratch the surface, namely to study the physics. After physics is understood, then only technology will come. Not that I am for technology, but it will come whether I like it or not. The interplay of the four fundamental forces which govern all the phenomena in the universe, these are the four fundamental forces. Many of you would have already seen it even in high school textbook. Let us start with the strong force, which is the strongest force known to us. Its strength parameter is order of magnitude unity. However, you will feel it only if you can probe less than 10 power minus 13 centimeter. Beyond that, it is zero. The force is zero. So it's the range is 10 power minus 13 centimeter. Now it is a strong force which binds the quarks to form the nucleons, namely proton and neutron. It is a strong force which binds the proton and neutron to form the nucleus. Next comes the electromagnetic force, which binds this nucleus with outer electrons and forms atoms. Atoms are bound by electromagnetic forces only to form molecules. Molecules are bound to form solids, liquids, and gases, and matter in all its forms by electromagnetic force. So electromagnetic force is the most important force. In fact, all the other forces, the phenomenological forces which you study in school or even in college, elasticity, viscosity, surface tension, all are manifestations of electromagnetic force. And its strength parameter is about 100 times lower than the strength parameter of strong interaction. And its range, in contrast to strong interaction, is infinite. That is the reason why it is all pervading, the effect of electromagnetism. In contrast to strong and electromagnetic force, weak force is a disruptive force. This is the force which is responsible for the decays of all the heavy elements. In addition, almost all the particles which I am going to talk about today decay only by weak interactions. But weak interactions have another very important role to play in nature. All of us are able to live because of the sun's heat and light, and the sun produces its heat and light through the weak force, through the thermonuclear fusion reactions occurring in the core of the sun. And similarly, all the stars shine only because of the weak interactions. And weak interactions also has a Demeter range. I have denoted it as, I have written it, its strength for letters. The strength parameter is measured by a parameter which is dimensions of inverse of the square of mass, and taking the mass of the proton squared as unit, it is 10 power minus 5. That is why it is called weak force. Its range also is limited. I have given the inequality less than 10 power minus 14 centimeter. Its precise range is known now. That is what happened after we constructed the standard model of energy physics. Finally, I come to the most important force of all, namely gravitation. It is because of gravitation that all of you are able to sit here, otherwise you will be flying in space. And it is gravity which binds you to Earth, and it is gravity which binds all the planets to the sun, and it is gravity which binds all the stars to form the galaxies, and galaxies are bound by gravity to form galactic clusters and so on. So, for the universe at large, it is gravity which wins. But if you look at the strength parameter, which is measured by Newton's constant of gravitation, again in units of mp square, it is 10 power minus 40. 38 orders of magnitude smaller than electromagnetism. Both are infinite range, but 10 power minus 38 times lower in strength. Still it depends. Why? I'm sure all of you know that. In contrast to electromagnetism, which can be made zero by having positive negative charges, because there is repulsion and attraction which can be cancelled. Gravity is always attractive. If you put more and more mass, it becomes more and more attractive. So all the heavenly bodies being very massive, 10 power minus 38 is getting compensated by the increase in mass. Now, this textbook classification of the four forces actually is broken down as a consequence of the development of standard model. Now we know that electromagnetism and weak don't stand alone. They are unified in the form of electroweak force, and electromagnetism and weak are two components of the electroweak force. And that unification suggests that maybe strong interaction also can be unified, and that has been called grand unification. At the moment, it is only a theoretical speculation because no convincing experimental proof has come. So I have put an arrow. For present, we are at this stage only electroweak unification is there, and standard model exists involving strong interaction and electroweak interaction. If still grander unification can come if gravity gets unified. That is called total unification. That was the dream of Einstein, but that has not yet happened. String theory might succeed in doing that, and I will talk about it a little bit towards the end of the talk. Since everything is based on electromagnetism, as I already said, let us start with electromagnetism. All of you should be familiar with this. The four Maxwell's equations are given here. Those of you who are studying electromagnetism or have studied, don't omit Maxwell's equations. Don't stop the course before you understand Maxwell's equation, because that is the sum of all of electromagnetism. That is the basis of electromagnetism. These four differential equations, I can go over each of these equations, but that will take time, so I will not do that. Gauss' law, Faraday's law of induction, Ampere's law, everything is contained here. These laws were Maxwell wrote them down on the basis of the experimental discoveries of many experimenters who had studied Ampere, chiefly Faraday. Faraday, in fact, because of his involvement with the experiments, he had a very profound idea about the electromagnetic field. He is the inventor of the idea of electromagnetic field, the field. In fact, Einstein somewhere says the greatest invention of the human mind is the invention of the idea of the field. Because now we know it is the field which dominates everything. All the basic theory which I am going to talk about contains the idea of the field. And Faraday was the author of that. Once Maxwell wrote down these four equations, which are the complete and consistent system of equations for electrodynamics, important consequences followed. Maxwell himself showed that electromagnetic waves are allowed to exist by these equations, and he could calculate the speed of those waves, and he found it is 3 into 10 power 10 centimeter per second. By that time, other scientists had already measured the speed of light, so Maxwell jumped to the conclusion that light is nothing but electromagnetic wave. This was an important discovery because until then, nobody knew what light was. Of course, they knew that it was a wave because of the interference and diffraction experiments of Huygens, Fresnel, Young, and so on. But what wave it was Maxwell who solved it. And soon Hertz experimentally could produce and detect the Hertz, the electromagnetic waves. Can I have some water, please? You don't see the water here. And then Jagdish Chandra Bose. I think today is the birthday of Jagdish Chandra Bose. Happens. I think. I saw it in the calendar. Anyway, it has to be checked. Anyway, Jagdish Chandra Bose and then Marconi and so on. All that history, all of you should know. Thank you. These equations have stood the test of time for more than 150 years. Even the two revolutions which I mentioned in the beginning of the talk, namely relativity and quantum mechanics, did not change these equations. In fact, it is Maxwell's equations which gave rise to relativity. In the confrontation between Newton's laws of particle dynamics and Maxwell's laws of field dynamics, Einstein took the side of Maxwell's equations and argued that they are the space-time picture consistent with Maxwell's equations are the correct ones, and then he had to change Newton's equations to be consistent with that space-time picture, and that is how relativity was born. So relativity, that is how E equal to mc squared came. Newton's equations he had to change, not Maxwell's equations. Even quantum mechanics did not change the equations, but quantum mechanics made a profound change in the meaning of this electromagnetic field. The classical electromagnetic field of Faraday and Maxwell, the energy exists as a continuum. I mean, any energy is possible, but quantum mechanics changed to discretization of the energy, electromagnetic energy. Energy comes in packets of energy called quanta, and it is those quanta which are called photons. And that is the birth of quantum field theory. And in quantum field theory, quantum field theory is the language of standard model, so I have to say a little bit about it. Let me give at least one example. How do we understand the electromagnetic interaction, the Coulomb interaction, for instance, between two charged particles? In classical Faraday-Maxwell theory, every charged particle like electron is surrounded by an electric field. But if it is moving, it is surrounded by a magnetic field also, by Ampere's law. And if you put another charged particle in the neighborhood, that feels this field and gets affected. That is how the Coulomb law and other electromagnetic phenomena take place in classical physics. How does quantum field theory change it? In quantum field theory, every charged particle like electron emits a quantum of the electromagnetic field, namely photon, which is indicated there by the wavy line and denoted by the Greek letter gamma, and that gets captured by another charged particle like proton, and it is this continuous exchange of the quanta of the field which is responsible for the force. So this is the basic understanding of all forces of nature according to quantum field theory. It's all emission and absorption and exchange of the quanta of the corresponding field. That is what you have to remember. This is a simple Feynman diagram. Feynman invented these diagrams to simplify the understanding of quantum field theory itself. I will be using them. So now we are ready to face the standard model of energy physics. It comes in two parts. One, the electroweak dynamics, which unifies electromagnetism and weak interaction. And strong interaction has been given a new name called chromodynamics, quantum chromodynamics. You can ignore those SU2 cross U1 and SU3. That requires some Lie group theory, but I will not need them here. So let us start with electroweak dynamics. Maxwell's electrodynamics is based on two fields, electric and magnetic field. And the electric field has got three components, because it's a vector, and magnetic field has got three components, so it is a 6-component field. In electroweak dynamics, these 6 components are repeated 4 times. I have indicated by that I don't know if you can see it. I'm sorry. Indicated by that I as a suffix over E and B. So electromagnetic field is repeated 4 times. One of them could be the electromagnetic field itself, whose quantum is the gamma I have indicated here, and the other 3 are quanta of the weak field. And the weak field has 3 quanta, W plus W minus are charged, and Z is neutral. These are the 3 weak quanta. I will explain at least one of them, one of the quanta, their role. As I already said, neutron and proton are made up of 3 quarks. Neutron is made up of 1 U quark and 2 D quarks. Proton is made up of 2 U quarks and 1 D quark. So in the beta decay of neutron, a D quark transforms itself into a P quark by emitting a W minus quantum. The other quarks only play a spectator role. And the W minus itself decays into electron and an antineutrino of E type. So that is the explanation of beta decay of neutron coming from the weak field. What about the dynamics of these fields? Oh, I have given some more Feynman diagrams. The first one is the electromagnetic interaction between two charged particles, the U quark and electron. Next, similar to that, W exchange, but here D converts itself into U and the neutrino converts itself into electron. So quantum field theory, you can see, not only explains forces, but a different kind of force in which particle nature itself changes. Not only that, in quantum field theory, the time is supposed to go in this upward direction, and so these are initial states, those are final states. And if you take a neutrino and put it on the reverse side, it becomes anti-neutrino. That is one of the rules of quantum field theory. So in the third diagram, D quark becomes U quark by emitting an electron and anti-neutrino. It's a decay of a D quark. That is what I have used in the explanation of the decay of the neutron. Finally, a Z type of exchange between a U and nu, and in contrast to the first diagram, that diagram gives an interaction force between U quark and the neutral neutrino also. So that much I think. These are the examples. What is the dynamics of the electroweak fields? And that is given in the box. You can see that they are very similar to Maxwell's equations. If you ignore those three dots, which I will come to later. So that is how this is generalization of Maxwell's electrodynamics. Now we come to quantum chromodynamics. The electroweak dynamics was a 4 times generalization. Quantum chromodynamics is 8 times. So there is a Greek index I have put which goes over 1 to 8, and their quanta and this field, this strong field, is called glue field. Why glue? Because it is this glue field which serves to bind the quarks to form tightly bound states like neutron or proton. That's why it's called glue field, and its quanta are called gluons. There are 8 gluons, and so that is the basic force which is responsible for the binding of quarks to form proton-neutron, and in some respect that is responsible for the binding of proton and neutron to form nuclei also. All the nuclei basically come from this force. And the dynamics again is a repeat of Maxwell's equations. But then question comes, if these are so similar to Maxwell's equations, why did we take more than 100 years to construct them after Maxwell? And the reason is contained in those 3 dots. For that I have to backtrack a little bit and explain further. See, electromagnetism, all of electromagnetism can be summarized in one line. Every charged particle is capable of emitting or absorbing a photon in quantum field theory. In classical field theory, it is capable of emitting, capable of having a field around it. Okay, every charged particle has that role. But what is charge itself? I hope you don't ask this question nowadays. Nobody can answer it. Nobody bothers about it. In olden days, it was a big question, what is charge? Benjamin Franklin even wrote papers and books on that. But now all that can be thrown into the sea because charge is a simple explanation now. Charge is nothing but a number which characterizes every elementary particle. Electron is negative charge, proton is positive charge. Some can have zero charge also like neutron. But it's a number. Now, I have introduced the 12 times generalization of the photon. Instead of photon of electrodynamics, we have 4 of them in electroweak dynamics, 8 of them here. 8 plus 4, 12. So 12 kinds of generalized photons. Okay, and correspondingly 12 kinds of generalized charges. These generalized charges are different from electromagnetic charge, electric charge in the following sense. If you take 2 charges A and B, they do not commute. A into B is not the same as B into A. Whereas for the charges A into B is the same as B into A. So these are non-commuting charges. Mathematicians call the algebra of non-commuting objects as non-abelian algebras, and that is why these are called non-abelian charges. And corresponding fields which are called gauge fields, I will not explain it because people who are studying electromagnetism would have to study gauge. What is gauge? Although many times that is ignored because of shortness of time, but don't ignore it. It is the gauge idea which has been generalized to construct the standard model. So these are called non-abelian gauge fields. These two of them. But I said in electromagnetism, every object which has charge is capable of emitting or absorbing a photon or capable of interacting with the electromagnetic field. But photon itself does not have charge. So photon cannot emit itself. So the theory of photon is a linear theory. Maxwell's equations are linear in the field. In contrast, these generalized photons, these non-abelian photons, themselves carry this generalized charge, and hence it is capable of emitting or absorbing itself. I have indicated non-abelian gauge. The theory of non-abelian gauge fields was first proposed by Yang and Mills in 1954, but it required many more steps before the theory could be used to construct the correct physical model, which is the standard model. So the first triple vertex I have given, a gluon, for instance, can emit another gluon or absorb it, and they can scatter also by a four-line diagram. So that is the theory, non-abelian gauge theory, and those dots contain these vertices. So I can actually expand the dots to explain to incorporate this. It's very simple. Only the equations will be longer. That's all. So the linearity of the fields is lost because of these two. Now this is the right time to talk a little bit about the quantized version of gravity, quantum gravity. Now what is the analog of electric charge in gravitational theory? I'm sure some student can answer it. What is the analog of electric charge for gravitational force? Yes? I'm sure all of you know it. All of you know Coulomb's law, and all of you know Newton's law of gravitation also. Yes? Mass. But that answer is not completely correct, because here we are talking about a relativistic gravity, namely Einstein's theory of gravity, in which the mass is incorporated in the total formula for energy, which includes the rest mass energy, E equal to root of m squared c power 4 plus p squared c squared. Okay? In that formula, it's the energy. When the kinetic part of it, the p squared c power 4 is small, we simply write E equal to mc squared, which has become the popular equation for Einstein's theory, but that is not the complete story. Okay? So it is the energy which is the analog of electric charge for gravitation. Now, gravitational field or the graviton, which is its quantum, it has been called graviton. Also is a physical object, so it has energy, and so it has to have self-interaction like the Yang-Mills field, like the gluon field. So a triple vertex exists and a quartic vertex exists. But in contrast to Yang-Mills theory, in gravitational theory of Einstein, once you write a four-line diagram, you have to add a five-line interaction, and that will add a six-line, and it is an infinite series. Of course, Einstein did not do this way. I have expanded Einstein's theory in terms of the graviton, but in Einstein's theory there is a neat expression based on Riemann's curvature tensor and so on, which is completely nonlinear. But it is this infinite series or the nonlinearity which has prevented the quantization of gravitational field. One might say that in physics we have, one might say Yang-Mills theory, therefore, in some sense, comes in between the simple Maxwell's theory and the very complicated Einstein's theory. Another way of saying that is, in physics we have progressed up to a non-abelian gauge theory, but we have not progressed enough to understand Einstein's theory. I have to say one thing more. I have put that red line, confinement. See, I said this is the theory of strong interaction, which is supposed to be the interaction between proton and neutron, between pi meson and so on. But nobody has seen a quark or gluon in experiment. Nobody has seen the track of electron, proton, etc. has been experimentally observed. But quarks and gluons nobody has observed. And that is explained by saying that the quarks and gluons are forever confined or imprisoned inside a prison of size 10 power minus 13 centimeter, namely the proton size. That is called confinement, and I would call it confinement hypothesis. that confinement is supposed to be provable from these equations, but the structure of these equations are so complicated that nobody has been able to prove. Although many attempts, many brilliant minds have been working on it, world's fastest computers also have been at it. In fact, if anybody can prove it, then he or she can claim a $1 million prize, because one of the 7 millennium mathematical problems posed in 2001 by the Clay Mathematical Institute in Canada is exactly this proof of confinement in Young's theory. Nobody has got it yet. I think I have to backtrack a little. I forgot to mention one thing. Yeah, something to do with the last column there. In quantum field theory, there is an inverse relationship between the range of a force and the mass of the quantum which is responsible for that force. Inverse relationship. And now, electromagnetism and gravity have infinite range, so the mass of the corresponding quantum, namely photon and graviton, have to be zero. Whereas strong interaction has a finite range, so its mass, the mass of the corresponding quantum has to be finite. And in fact, Yukawa, even in the early 30s, had predicted the existence of that quantum as pi meson, about 200 times as heavy as the electron, and that was experimentally observed later. But the strong interaction, the story does not stop there. We have to go up to the PCD. And in weak interaction, I said that the force again has a limited range, so its quantum, namely W plus, W minus, and Z, have to have finite mass, in contrast to the photon. I think I have more or less finished. Yeah, this is the last transference for standard model. The universe consists of two components, the physical universe. One I have called the field sector, and we have already introduced the fields, photon, the electromagnetic field whose quantum is photon, and weak field quanta W plus W minus Z, and the 8 gluonic quanta for strong field. Then there is one more quantum called the Higgs boson. I will say a little bit more about it. And all these particles, photon and the 12 non-abelian gauge bosons, have spin 1. Remember, electron has spin half, you might have studied. Photon has spin 1, and all these have spin 1, whereas the Higgs boson has spin 0. So all these have integral spins in units of h cross, 0 or 1 or 2. They are called bosons, and they satisfy Bose-Einstein statistics. It was Satyendranath Bose who discovered the bosonic nature of photon first, and that was extended to other particles, more generalized by Einstein. So the statistics obeyed by bosons is called Bose-Einstein statistics. Of course, G mu I have indicated below a dashed line because quantum gravity still does not exist. But once we succeed in quantizing gravity, its quantum is called graviton, that will have spin 2. Now let us come to particle sector. Let us start with proton and neutron, which are made up of 3 quarks each. I have already indicated U and D quarks. And put U and D as one column I have put. That's the way it comes in standard model. And once you have U and D, you can make proton and neutron. Once you have proton and neutron, nuclei can be made, and if you include the electrons, atoms can be made, molecules can be made, all matter can be made. If you include the neutrino also, which I have put above the electron symbol, then thermonuclear fission reactions can happen in sun, and life becomes possible. So with that quartet of particles, the first column is called the electronic doublet, neutrino and electron, and the quark doublet U and D. With these 4 particles, a very complete universe can be formed. Still, for some very important reason, which I will not go into today, I may indicate it, but not detailed, nature has decided to repeat this quartet 2 times more. In addition to electron, a heavy electron, actually it was Homi Bhabha who first discovered this heavy electron called muon, and then a tauon, which is even heavier. So 3 leptonic doublets, and then heavy quarks also have been discovered. So there are these 12 particles. they all have spin half integral unit. Any elementary particle like electron, which is spin half in units of its cross, is called a fermion, and they satisfy Fermi-Dirac statistics. I have to add one more column for the antiparticles. Now, when the universe started in the Big Bang, all these particles were produced in equal number, all of them are equally important. Only thing is, all these heavier particles, the heavy electron and the heavy quarks and so on, they have all decayed by weak interaction. That is another important role of weak interactions. And they are removed from the universe, leaving the universe to be finally constructed out of U, D and electron only. In addition, there are antiparticles, anti-electron, which is positron, anti-quark. So I have to put another column. They also were produced in equal number. Particles and antiparticles were presumably produced in equal number in that big explosion, which we call Big Bang. But now we don't see any of those antiparticles. They have to be produced in the lab. Of course, they exist because they can be produced in the lab and they are being studied. But universe is not, in the universe we don't see. Naturally we don't see. What happened to them? So there is supposed to be a matter-antimatter asymmetry, which is supposed to have removed the antiparticles. And that matter-antimatter asymmetry is possible only if there are these three quartets, three generations they are called. So that is the importance of the three generations. One last remark on this transparency. Although I have called it field sector and particle sector, you can see that that name is wrong. Because fields also have particles, quanta are particles. Similarly, the fermions also are quanta of the corresponding field. Electron is a quantum of the fermion electron field. Quarks are quanta of the quark field. In quantum field theory, the field is the primary thing and quanta exist. So particles and waves, the old particle wave duality gets completely explained only in quantum field theory. So the correct way of distinguishing these two sectors are bosonic sector and fermionic sector. That should be the correct way. I think that is the end of. If you think that I have explained the standard model, you are completely wrong. In order to explain standard model, one has to go over this. Each and every item here has to be understood. Because mathematics is the basis of physics, please remember. No amount of talk will do. And this requires a full course in quantum field theory. So we cannot do that. But I am not trying to frighten you, but that is the real nature of reality. If you want to understand reality, you have to learn this. That is the challenge. Another reason why I like this slide is that when I started my life in particle physics 60 years ago, we were all groping in the dark. We did not know what weak interaction, at least we had the help of Fermi's theory, which already existed, but strong interaction was a complete black box. Still we did research and we even got our PhDs and wrote papers and so on. I never thought that one day we will be able to put the basis of all of physics, all of high energy physics in one page. So that is the reason why I like this. So that is the degree of progress in physics, in fundamental physics. Yeah, this is also part of that. So the standard model which I have described so far was constructed by theoretical physicists more than 40 years ago. Experimenters verified each component of this theory in the next 40 years except for one component, namely the Higgs boson. This last missing piece was discovered only in 2012 and that was big news. Standard model emerged as the standard theory describing all of nature. Where do we go from here? Remember, standard model is a theory of only three fundamental forces. The fourth force, gravitational force, is missing. So now I say a little bit about quantum gravity. It's a deep irony of nature that the twin revolutions of quantum and relativity that powered the conceptual advances of the 20th century and that underlie all the subsequent scientific developments have a basic incompatibility between them. In other words, the marriage between quantum mechanics and relativity has not been possible. By relativity here, I mean general theory of relativity, since Special relativity has already been combined with quantum mechanics, leading to quantum field theory, which has been used in constructing the standard model. Gravity, which gets incorporated into the very fabric of space and time as curvature in Einstein's general relativity, has resisted all attempts at being combined with the quantum world. Excuse me. Hence, quantum gravity has become the most fundamental problem of physics. The most successful attempt to construct quantum gravity is string theory. Actually, string theory offers much more than a quantum theory of gravity. It provides a quantum theory of all the other forces too. In other words, it can incorporate the standard model of high-energy physics also within a unified framework that includes gravity. So I will say a little bit about string theory. In string theory, a point particle is replaced by a one-dimensional object called string as the fundamental entity. Its length, it can be an open string with open ends or closed string, and its total length is about 10 power minus 33 centimeter. 10 power minus 33 centimeter, which is the length scale of any theory of quantum gravity, including string theory. Compare it with 10 power minus 17 centimeter, up to which we have reached. But this requires 10 power minus understanding down to 10 power minus 33 centimeter. The various vibrational modes of the string correspond to the elementary particles. String theory automatically contains quantum gravity, and that is its special beauty. Remember, in quantum field theory, we could not include gravity in a reasonable way. But here, you cannot construct the string theory without gravity. However, this is bought at a price. It works only if the number of space dimensions is 9 and including time it is 10. Where are the extra 6 dimensions? They are curled up to form space bubbles at distance scales of the same 10 power minus 33 centimeters. Both the string and the extra curled up dimensions will be revealed to us only if we can access such length scales. So, has string theory solved the problem of quantum gravity? Yes, perhaps. But how do we know? Where is the experimental support for string theory? Remember, it took 40 years to verify the standard model as the correct theory of nature. It was constructed roughly in the 70s, and 2012 only even the Higgs boson was discovered. So it took 40 years or more. In fact, if we start with Fermi's theory of weak interaction, which is 1930s, you can see it took more than 70 years to construct the standard model from the beginning. That required the construction of particle accelerators and particle colliders of higher and higher energy, ultimately culminating in the construction of the Large Hadron Collider LHC at CERN Geneva, reaching energies in the TeV region, namely 10 power 12 electron volt. This machine is very huge. It is a behemoth. It has a circumference of 28 kilometers, and its construction took 20,000 physicists and engineers working for 20 years. Many Indian physicists and engineers also were involved in it. In relativistic quantum mechanics or quantum field theory, there is an inverse relationship between the length scale and the energy required to probe it. The energy required to probe a length L goes like 1 over L. So it's exactly like a relationship which I mentioned earlier between the range of an interaction and the mass of the exchange quantum. Remember, I said at the beginning of the talk that we have descended down to a length scale of 10 power minus 17 centimeters. To probe this, we needed the TeV energies of LHC. So, to probe the length scale of quantum gravity, namely 10 power minus 33 centimeter, we need 16 orders more energy, 10 power 16 TeV. This is the energy required to experimentally test string theory or any theory of quantum gravity. Most people think this is not possible. This is the crisis in fundamental physics. Galileo had decreed laws of physics are written in the language of mathematics, but those laws can be proved or disproved only by experiments. For 400 years, physics has progressed only by following this path laid out by Galileo. If we give up this path now, that will be the end of fundamental physics. In that case, all the beautiful theories that have been built for quantum gravity, including string theory, will remain as mere metaphysics. What is the way out? I have a few remarks on cosmology. I will omit them because of lack of time. We have to make a direct attack on this high energy frontier. Instead of merely scaling up the sizes of the accelerating machines beyond 28 kilometers, it may be impossible. They may go a little bit higher. In fact, there is a plan to construct a percent accelerator can go up to 14 TeV, one order of magnitude more. 100 TeV accelerator also is being designed by CERN and other countries, and maybe we can go even up to 1000 TeV. Beyond that, even the whole Earth's circumference will not be enough to have an accelerator. So either new principles of acceleration have to be discovered, or there will be end to high energy physics by about 2040. That will be the end of the road in fundamental physics by about 2040. This conclusion is nothing to do with quantum gravity or Planck energy, 10 power 16 TeV, because beyond about 1000 TeV, the present methods will not work. But if you look at the growth of accelerator energies over the past 80 years or so, it has been phenomenal. The energy has been increasing by a factor 10 every 6 years. I interpret this exponential growth as an optimistic sign for the future of fundamental physics. So if the same growth can be maintained, 16 powers of 10 can be reached in 96 years. 96 is not too long in my opinion, because we took 40 years even to detect the Higgs boson. But this is possible only if new principles of acceleration and newer technologies are continuously invented. And this increase in accelerator energy is plotted as a function of energy. It's called Levinson plot. That Levinson plot is a straight line in the logarithmic plot. And that straight line actually is not the straight line for any single type of accelerator. Any single type of accelerator, the energies go like that and then saturate. The next invention takes the energy once more and again saturates. So that straight line is the envelope of this. So that means newer and newer technologies have to be continuously invented. So what are the new principles of acceleration? I will give one example. In the last 30 or 35 years, many ideas on laser plasma acceleration are being pursued all over the world. Using laser excitation of plasma wave fields, electrons have been successfully accelerated to 1 GeV, namely 10 power 9 GeV, in 1 centimeter compared to kilometer size conventional accelerators to get similar energies. So tabletop accelerators are perhaps not far away. Maybe this will lead to breakthroughs that will help us to cross the super high energy barrier. Of course, laser plasma acceleration alone is not enough to go up to Planck energies, but this will be an important step. Actually, what we need are 100 crazy ideas. Maybe one of them will work. Maybe the breakthrough will come from one of you who is technologically and physically, scientifically oriented. And one of your bright ideas might work. So this is an important field, excellent opportunity and challenge for experimentally oriented students. I have said something more about strings here, but I think I will omit them. I have to say a little bit about Higgs. Again, remember the vast disparity between the range in electromagnetism and the weak force. One was infinite, another was finite. And in spite of that, electromagnetism and weak force have been unified. How does that happen? This is achieved by what is called spontaneous breakdown of symmetry, SBS, engineered by the celebrated Higgs mechanism, which keeps photon massless while raising the masses of W and Z to finite levels. Actually, the theory has W and Z masses now around 80 and 91 GeV, precisely at the theoretically predicted masses. Again at CERN in 1982, those were discovered, experimentally discovered. So those were already great triumphs for the Standard Model, the W and Z. So using these precise masses 80 and 91, you can, using the relation which I already mentioned, you can get the range of the weak force, and that comes out to be some particular number which can be easily calculated into 10 power minus 15 centimeter. Well, the idea, I think I don't have time to describe all this, but the main contribution is Higgs, and there were many others. Higgs paper was 1964, but there were many others. In particular, I will mention Kibble. Higgs did it only for the abelian theory like electromagnetism, but it is Kibble who generalized it to non-abelian theory, which is what was used in constructing the standard model. So electroweak part of the theory is called Glashow-Salam-Weinberg model because of their contributions. But let us come to some physics. There is a bonus. Higgs mechanism postulates the existence of a universal all-pervading field called the Higgs field, which is supposed to exist everywhere. It's a universal field which exists everywhere, and it is because of this only W and Z get mass. Not only that, even the masses of all the fermions like electron and the quarks get mass only through the Higgs mechanism. Except for one variety of particles, namely neutrinos, they do not get mass at all. They remain massless in spite of the Higgs mechanism. Higgs mechanism gives mass to everything in standard model except to photon, of course, and to neutrinos. That's an important byproduct of the Higgs mechanism, a massive spin zero boson, which is actually the quantum of the Higgs field, which has been called Higgs boson, that should exist, and high energy physicists searched for it for many years, and finally they succeeded in getting it in 2012. I already described it. I think all this I have already mentioned, I don't have to repeat. Some more about Higgs mechanism. Now I have to say a little bit more about, so once the Higgs mechanism established the standard model, that is not the end of the story because there are still many more things. Let me first talk about neutrinos a little bit. Neutrinos are massless in the standard model. As I already mentioned, Higgs mechanism does not give mass to the neutrinos. About 20 years ago, experimenters discovered that neutrinos do have masses, although very tiny. And this has been hailed as a great discovery because this may show us how to go beyond standard model. Neutrinos may be the portal or the window to go beyond standard model, and that is the importance of the India-based Neutrino Observatory (INO), which is which is supposed to come up in Tamil Nadu. Next, dark matter. Astronomers have discovered that most of the matter in the universe is not the kind we know. It is not the things which we have been talking about in standard model. It is called dark matter since it does not emit, absorb or scatter light. Although this discovery has been made already by astronomers through gravitational interactions of this dark matter, nobody knows what this dark matter is about, and only physicists can discover it. And for the last 20 or 30 years, many experiments have been mounted to really detect this dark matter particle, but nothing has so far succeeded. And this dark matter experiment also will be mounted inside the INO cavern. Other things, in the last 4 decades after the standard model was constructed, theoreticians have not been idle but have constructed many theories that go beyond the standard model of this grand unification which I already mentioned. Another is supersymmetry, which postulates the existence of a boson corresponding to every known fermion and vice versa. For electron, there is a bosonic electron. For photon, there is a fermionic photon. This is a very elegant symmetry that leads to a better quantum field theory than the one on which standard model has been built. I am not talking about the bad part of the quantum field theory, which are the divergences. In spite of the divergences, standard model has been constructed, but this supersymmetric quantum field theory is a better quantum field theory, and that is why theoreticians like it. But if it is right, we have to discover a whole new world of particles equaling our known world. For electrons and quarks corresponding bosonic objects, photon and the other gauge bosons corresponding fermionic partners. And remember, we took 100 years to discover the known particles, starting with electron. So more patience is needed to discover supersymmetry. There are many more theoretical speculations apart from grand unification and supersymmetry, but none of them has seen an iota of experimental support so far, even in the Large Hadron Collider. However, Large Hadron Collider will have many more years of operation. It is still alive. Let us hope that new things will be discovered. Of course, the biggest loophole in standard model is that gravity has been left out, and I have already talked about it. Yeah, I think that is the last transparency. The various people, both the theoreticians and experimentalists who have contributed to standard model, many of them have been awarded Nobel Prize, starting with Rajasekaran, Weinberg, and ending with Higgs and Engle for Higgs mechanics. Yeah. Thank you very much for your patience. I have time for, I think we have time for a few short questions. Mishra ji?
Yes, sir.
Yeah, if there is any question, I would like to answer them. You can ask any question. Unless everything was so clear. That's not possible because so many things I have compressed. It is supposed to be in Theni district. Yeah, in fact, that is a big shameful thing in our country. We talk very highly about our science. A project of this magnitude, of international type, which was planned right in this institute in 2000, is almost 20 years. 20 years we have been working on it, it's still not taken root. We have still not dug it. It is supposed to be a cave one, dug inside a mountain in Bodhi Hill in Theni district near Pottipuram. And some people, they call themselves environmentalists as if they are the only people who are bothered about environment. They raise all kinds of objections which have nothing to do with science, scientific fact. We have been trying to answer all their criticisms. They go on repeating it ad nauseam. And some politicians also have joined. So it has become a big controversy. It is unnecessary. You see, it is INO is a scientific lab, like a lab in IIT or a big experimental institution. It is like central government giving a new IIT in Theni district. Will the Theni people object against it? They will open their arms to welcome it, right? Instead of that, these politicians and so-called environmentalists have spoiled the whole atmosphere. We are fighting it. It will come. Only thing is it's getting delayed in Theni district. Any other question? That requires a separate discussion. So, unfortunately, we wanted to include one talk on neutrinos and INO. We didn't have space. Any other question? Yes. Pardon me?
Neutrino does not interact with Higgs field.
No.
But how did they get neutrino at tiny mass?
That will involve one talk. In fact, originally I could have given that talk. There is a thing called neutrino oscillations. See, neutrinos are produced in the sun, they come here. But the amount of neutrinos which come is about 1/3 of what theoreticians calculate. And then the so-called atmospheric neutrinos, cosmic ray neutrinos, there is also there is an anomaly. These anomalies are explainable in terms of neutrino oscillations. I told you neutrinos come, I did not tell you, but when I talked about the fermionic sector, along with the electron, one neutrino, which we call nu e, along with the mu, another neutrino, nu mu, along with tau, nu tau, three kinds of neutrinos. One neutrino is capable of turning itself into another neutrino. And that transition is possible only if neutrinos have mass. So all those transitions occur experimentally observed now, and hence mass exists. That is the discovery of the neutrino mass. So neutrino mass exists, but that mass turns out to be very, very small. See, I will give you an order of magnitude. The lightest elementary particle known is electron, 0.5 MeV. Neutrino mass is a fraction of an electron volt, million times smaller. Nevertheless, it is massive now, and you have to explain it, and for that you have to go beyond standard model. Any other question?